So this should have been fairly easy, taking care of ions and standalone atoms. Okay, were there no questions on this quiz at all? Everybody understands everything 100%. Well, that is amazing. I'm going to close this out then and open up the PowerPoint for today. So let's see if we can share a different screen here. All right. So we're kind of getting into the concept of bonding here, which I think is a chapter that a lot of students have been looking forward to already, because I think a big bulk of chemistry is understanding the bonds between atoms, right? And the reason we're doing this after the atomic structure is because now you guys understand that the electrons of an atom, they share various orbits, right? There's inner orbits, there are outer orbits. You have a better idea of what the interior of an atom looks like. And as a result, you will be more suited to understanding how atoms will combine with one another, right? And a lot of their ability to combine will have to do with electrons. Those outermost valence electrons are going to be playing a very big role in the bonding situation, okay? Now, let's see, before we get into that, I do want to take attendance actually. So I'll let you guys think about these 3 questions here. What is meant by the term, the idea of chemical bonds? Why do atoms bond with each other? Okay. And how do atoms bond with each other to form these compounds? Okay. So I'll let you guys ruminate on those questions for a little bit while I take attendance. So here's 8221. Wang, Chen, Dornall. Anna Sherman. All right, so it looks like we've got everybody but one. Let me just lock that in. And I'm also going to unlock the module for this class so that you can see those CK12 assignments. All right. So hopefully we're going to answer most of these questions by the end of today's lecture. I'm sure you guys recognize this compound here. It is quartz, okay? And the bonds between atoms in the quartz metal-ish are going to be very strong, right? So we'll see some examples of very strong bonds and very weak bonds as we go along. So what is even a chemical bond? We basically want to create molecules, right? We're going from the step of atoms to molecules, and we want to figure out, well, how did we get to that point, right? Scientifically speaking, they did not really necessarily define anything on a fundamental level, but basically there will be various forces, primarily due to the, positive and negative charges within atoms that will cause atoms to get together, basically. And as I implied in the previous week's lectures, atoms will tend to, or even electrons will tend to want to be in the lowest energy level state, right? Remember, we had the s orbitals, the p orbitals, the d orbitals, the f, right? Once electrons get into the f orbital, it takes a lot of energy to get to that point, right? Electrons don't necessarily want to be in that orbital. They do like to be in the relaxed ground state, which is what the s orbital, spherical orbital represents, okay? It's kind of the same thing with atoms, right? So atoms will combine, or really they're ions because most of them are charged. They will combine with other atoms if they find that they can be in a lower energy state, if they're combined and forming molecules instead, right? So for example, if we have the Na ion and the Cl ion, well, those are negatively and positively charged. Well, if they come together and transfer electrons and become neutral, then both atoms are going to feel more relaxed. Okay. Now this distance between the nuclei is a pretty major concept that will be fleshed out probably in a real chemistry course, but for our purposes, it's not really that important. Okay. That's because I don't want to get too much into the electric physics side of things here. So if we use Coulomb's law, if you guys took chemistry, sorry, I should say physics before, they did mention Coulomb's law with regards to charges, right? And the distance between charges and the magnitudes of the charges will determine the length between these two nuclei, okay? And if you pop into a chemistry textbook, you'll see tons of tables filled with a list of all these various lengths. Okay. Now, to understand why or in what way two atoms are going to combine, we want to think about how the positive charges and the negative charges kind of balance each other out. And the best way to do that is to determine the interaction between two hydrogen atoms to form H2, right? So if we've got two hydrogen atoms that are kind of far apart from one another, there's not really going to be much interaction between their electron clouds, okay? Now, I know it looks like each atom has multiple electrons. That's obviously not true. This is just the probability distribution of where its electron can possibly be, okay? And if they get pretty close to each other, well, what happens? The electrons of one atom are going to start to be attracted to the nucleus, which is positively charged, of the other atom, right? We've got a bunch of negative stuff happening around and the positive stuff happening internally in the nucleus, okay? And those are going to be sufficiently attracted to each other so that they'll start to move in, right? But they're not going to move in all the way because these positive portions of the nucleus, those will be repelling each other, right? So even though these floating negative charges are attracted to these nuclei, the positive charges of the nucleus, once they get together, they're going to want to push back a little bit, okay? So that's why every binary compound is going to have a sweet spot with regards to the distance between the two nuclei. And they will have a specific length, right? Distance between those two nuclei. And keyword here is optimum distance for lowest overall energy of the system. So like with anything else in the universe, we're going to want to be in a low energy situation. Okay. So let's see what that looks like graphically. Okay, this is a common graph that we will see throughout these kind of chapters, right? And basically what we have here is the x-axis is the distance, right? The distance between the two nuclei. And on the y-axis, we've got the energy, okay? Specifically potential energy or chemical energy, really, associated with those distances, right? So over on the left, we can see that if these two hydrogen atoms are extremely close to each other, it's going to have a very strong potential energy. You can actually liken this to magnets, right? So magnets and positive negative charges is very similar. The north-north parts of our magnet, if you try to put two norths together, they are going to want to repel, right? There's energy associated with it. You have to hold them together. If you let go, those two north sides of the magnets are going to repel against each other. Okay, so that is associated with a positive potential energy charge. If they float away from one another sufficiently such that they've got a sweet spot, this is a 0.074 nanometers distance, the bond length between these two nuclei, then we'll actually have a negative potential energy of negative 458 kilojoules per mole. And this situation, right, these atoms are going to want to stay there, right? They're going to want to stay that specific distance apart. And in order to pull them apart, it's actually going to take energy, right? It's going to take energy in order to get these two hydrogen atoms to pull apart. That's what the negative kind of represents there. Now, if these guys move further and further away, they're still pretty happy, but the energy situation is not really optimized, okay? And if they're super far away, like in this point, then the potential energy associated between that interaction is essentially zero. Okay, so indeed here, this 0.074 is measured in nanometers. Okay. Are there any questions on this?
Is this just for hydrogen?
No, this is for any binary compound.
Okay.
And if it even gets more complicated with like 3 or 4 atoms within a molecule, right? So that is super advanced university level chemistry stuff. This is just demonstrating the relationship between energy and distance between nuclei in general.
Thank you.
Okay. All right, so what are some key ideas behind bonding? Again, we've had multiple different types of bonding situations that we kind of touched upon in earlier weeks. First off is ionic bonding, in which electrons are totally transferred from the negative ion to the positive ion in order to create a solid unit, which is neutral, okay? Covalent bonding, I'm sure you've heard of this, very strong bonds. They are done with sharing of electrons, right? So electrons are not transferred, but they are shared between two nuclei, and there's a handful of electrons that are not necessarily belonging to either one of the atoms. And then we're going to talk about some intermediate cases that are kind of in between covalent and ionic bonding, in which there's still kind of a unbalanced distribution of electrons. Okay. So these bonds will actually play a very large role in the chemical behavior of these molecules, right? So for example, here we've got graphene in our pencil tip, right? And what we're trying to demonstrate here is that the bonds between these carbon atoms here are actually very loose, right? Very loose bonds, probably not covalent, right? And so for that reason, these substances are very easy to wipe off, which is why it's practical for usage in a pencil or maybe chalk, right? So what is the intermediate case? Well, that is a pretty typical situation in which we have a polar covalent bond. Okay, and I'll show you guys some images of what a covalent bond looks like eventually, so that you can kind of get an idea of how to visualize this. But it's basically the unequal sharing of electrons between atoms in a molecule. And as a result, one side of the molecule is going to be a little bit more positive, and the other side of the molecule is going to be a little bit more negative. Okay, so these are partial or fractional charges, right? So one very common example of this is H2O. So we've got a super negative oxygen combining with a couple positive hydrogens. And as you can see here, we've got a gradient by how strongly these electrons are being pulled towards the oxygen. Okay, any questions with that? Hopefully this explains the shape of an H2O molecule fairly well, right? One of these electron guys is hanging out towards the oxygen, right? So the hydrogen actually does not have many electrons near its nucleus, near its proton. So it's still going to be slightly positively charged, and the oxygen is going to be slightly negatively charged because it's trying to pull those electrons closer to itself. Okay. This is often represented by these special symbols here: fractional negative charge, fractional positive charge. Okay. And how did scientists or chemists really determine this? They would throw these compounds into an electric field that was created by a parallel plate system, right? So if we've got like a binary compound, let's say a very strongly ionic binary compound with hydrogen and fluoride, okay? Initially, as far as they know, these molecules are just pointing in every which way. But if we induce an electric charge on these two plates, one of them positive, one of them negative, all these binary compounds are suddenly going to line up, right? They're going to line up in accordance with the electric field, right? So the positive side is going to be attracted to the negative plate, and the negative side, which is probably the Cl, right? No, the fluoride, sorry. That's going to be attracted to the positive plate. So it's using these electric fields that chemists were able to determine, whether or how strongly ionic these bonds are. All right. So hopefully we will able to absorb these concepts. I do want to get into some conceptual questions here. What is meant by the term chemical bond? Again, very loosely defined. I don't want you guys to answer this one. It's a little dumb. But basically there are various forces, okay, electric forces that will cause atoms to move in with one another so that they function as a unit, aka a molecule. Okay. And honestly, for most of this lecture, we'll be dealing with binary compounds. So more advanced looking molecules, we're probably not going to be dealing with too much. The other two questions I want you guys to answer is, why do atoms bond with each other to form these molecules, and how do they bond with each other? So what are the different types of bonds? So this is definitely a very conceptual written type of question, but I will give you guys about 3 minutes to pop in some ideas, just summarize in your own words into the chat box. And once I see stuff, I will respond accordingly. Or get you on the right path. Okay, I've gotten 2 direct messages regarding the first questions. So yeah, things about like the octet rule and valence electrons, those are things we'll talk a little bit about later. Octet rule will actually be towards the end of this week. But just based on what we've talked about so far, think a lot about energy, right? All right, guys, I really want more than 3 answers here. The previous class was way more active than this. All right, think about energy levels, think about relaxed states. All right, well, it sounds like some students are just gonna have to review this stuff because I really just have to proceed here. Atoms do bond with each other to form molecules because they find that they're in a lower energy state, right? Okay, a few more direct messages. That's nice. Again, we don't really need to do this first question here, right? So right. And how do they bond with each other? Okay. That is basically either the transfer of electrons or the sharing of electrons. So the behavior of the electrons in the outer shell are really what's going to dictate their behavior. Okay. All right. One thing to keep in mind here is that these chemical reactions or bonds, they are occurring within a molecule, right? So we're not really talking about interactions between molecules, right? If you learned it in like biology, inside of a cell cytoplasm, there's all different kinds of like proteins and enzymes and things like that that are interacting with one another. These are molecules that are different and still have interactions, but chemical bonds are always within its own molecule, right? Only between the atoms that are connected to each other. And it's not only the type of element that is within the molecule that is going to determine the chemical properties, right, of this molecule. We also care a lot about the bonds, which will play a role in how reactive or flammable the compound is. Okay. So I will roughly show diagrams that show what an ionic bond looks like, what a covalent bond looks like, what a metallic bond looks like. A very common example of an ionic bond. And by the way, metallic bonds we're not going to be talking about too much. There's not much like math involved with this one. It's a kind of a unique case. And in most high school chemistry classes, they don't really deal with transition metals all that much, okay? So I would say that if you want to prioritize things, covalent bonds are the most important bonds. Ionic bonds may be the next most important, and then metallic are probably something you can gloss over for the most part when it comes to your high school classes, okay? So here we've got NaNCl. This forms a ionic compound, and notice how the atoms are completely separate from one another, okay? In this part, we've got covalent bond, okay? This is actually between itself, right? Oxygen and oxygen. Some of you might know this already, but oxygen has 6 valence electrons in its outermost shell. And 2 of them are going to be shared, right? So 2 of the blue guys from the right-hand side and 2 of the red guys from the left-hand side are going to be shared with one another. And this is a full-blown covalent bond. Metallic bonding, again, is something that I'll gloss over, and that is because electrons themselves, they gloss over the nuclei of the metallic bonds that are so closely tied together, right? So the thing about metallic bonding is that these electrons are not necessarily tied so closely to any particular atom. It's kind of like floating along a sea of positively charged nuclei, right? So they kind of mush together. And for that reason, the dynamics are very complicated and therefore not really talked about very much in a high school chemistry class. Okay. Any questions about these diagrams? Okay, I'll show you guys a better representation of ionic bonds with an animation later on. All right, no questions. Very good. I do want to bring up the concept of electronegativity, which will pretty much dictate the rest of this lecture, honestly. And basically, every atom in the periodic table is going to have different levels of being able to pull electrons towards itself, right? So some atoms are going to be very weak in terms of them being able to pull in electrons from the environment. Other atoms are going to be very strong in their ability to pull in electrons, okay? So that's what they mean by affinities of atoms for electrons, right? Kind of a word salad here, but ability of an atom within a molecule as well, right? Not only is it on their own, but even within molecules. And that will actually play a very large role in pulling electrons from one atom to another, right? The charge distribution, okay? So HX, again, just hydrogen and any other random element. They're going to be determined by, basically, we're just going to have tables of this stuff, right? So there will be tables that tell us what is the exact electronegativity of each element, and kind of by comparing them, we will be able to determine what type of bond is going to be formed. Okay. So what is a good reference table for all these electronegativity values? Some textbooks will have a table or a list rather. This one is in the form of a periodic table, okay? And as you can see, every single element has its own EV value, okay? So up here, these EV values are fairly high. They are very greedy. They want to pull in electrons. And the EV values for these, earth minerals, metals, are kind of low. Right? They're a bit weaker here. So this is really yet another periodic trend that we can look at. Last week, Thursday, we talked a lot about periodic trends. And this is just another one that we can add onto the list. Okay, it's very closely related to the concept of electron affinity and ionization energy, right? Ionization energy and electron affinity is kind of the same thing, and they will follow the same patterns. Okay. So the key here is we want to compare our EV values, right? So if we take two various elements, right, and we compare their EV values, that was going to be called the electronegativity difference. Okay, so Cl and Cl, we'll start from the left here actually. Cl and Cl, they have the same exact electronegativity, so obviously the difference is going to be 0. So this is going to be a fully wholesome, equally shared electron situation. So it is a pure covalent bond. On the other side, we'll kind of get into the extremes first. The electronegativity difference could be greater than 1.7. This is what was determined by most chemists to be kind of the boundary point between what constitutes as a fully ionic bond. And of course, Na and Cl, that is a very typical example of a ionic bond because Cl is way on the right-hand side of the periodic table. Na is way on the left side of the periodic table. So therefore, it's going to be a very large difference in electronegativity values. And of course, there's going to be a mid-range situation in which our difference in En is not kind of in the middle, right? Maybe it's 1, 1.2, even 0.7 or so. They will still have a covalent bond. It'll be defined as a covalent bond, but the distribution of electrons between the nuclei of the atoms is going to be uneven, right? So this hydrogen here is going to still be a little bit positive. The Cl over here is going to be a little bit more negative. Why is that? Because the Cl is more electronegative and it's going to be pulling in more of the electrons to its side, causing it to become more negative. Okay. One thing I find strange about this diagram is it does not tell us what happens between if it's just less than 0.7, right? So if we take this 0.7, honestly, based on most literature that I've seen, as long as the difference is even less than 0.7, like 0.5, 0.4, that will actually be considered a purely covalent bond, right? There might be some slight uneven charge distribution there, but for the most part, practical purposes, we can define it as a covalent bond, right? Because otherwise, it would be only binary compounds that are of the same element would be having covalent bonds, and we know that that's not necessarily true. Like nitrogen and oxygen, those are right next to each other on the periodic table. They will obviously be forming a covalent bond, and the electronegativity values will not be 0, but still be very small. Okay, so I'm going to give you guys this magical diagram very soon. The trend is that it's going to increase across a period, that is to the right, and electronegativity will decrease as it goes down a group. And the range that we saw in the previous diagram was between 4.0, so fluorine is the most electronegative, aka the most greedy for electrons, and cesium, and I think another guy below cesium, were also extremely low on the negativity scale. So what are these electronegativity values visualized? It's right here. Okay, so very similar to the periodic trends table that I showed you guys last week. As we go to the right, these elements are going to get stronger, so to speak. As we go to the right, they'll get weaker. Same thing with going up and down. As we go up, the elements will get stronger. The more down we go, the weaker the elements will become, the less they care about pulling in electrons from other folks. Okay. And this is primarily telling us what the relationship will be like between two elements after they've already formed a molecule, after they've already formed a compound. Okay, any questions about this magical table?
Do we have to memorize this or no?
Definitely do not memorize the values, right? But the general trends you should memorize. I don't think any textbook question is going to be that big of a douchebag in which they'll try to trip you up with the gold, right? We see here with the AU, the gold is actually an anomaly, right? It's actually very high electronegativity, even higher than these folks way towards the right. So again, there are some anomalies here and there, but I'm pretty sure that even in an AP chemistry course, they will only make sure that you understand the trends, right? So again, we're kind of repeating the rules with electronegativity, right? So try to screenshot these rules. Anything greater than 1.7 will be defined as ionic. If it's between 0.7 and 1.7, it'll be polar covalent. And then if it's really low, closer to 0, it's going to be practically fully covalent. Right. So this number line here is actually very useful. So as we go very, very large in our delta E, right, it's going to become more ionic. If our delta E gets closer and closer to 0, we're going to have more increasing covalent behaviors. Okay. Another way to visualize this, I think I've shown something similar already, is the electronegativity and bond types, right? So the more to the left we go, this is fully covalent. This will happen if it's a binary compound of the same element, right? Otherwise, there will be some fractional charges. And if it gets too big of a difference between the electronegativities, we'll have positive and negative fully ionic bonds. And in this case, electrons are transferred. So I know the text is very hard to read, but electrons are actually transferred when we deal with ionic bonds, okay? And that's also kind of why it makes them very weak, right? If we're transferring electrons, we're not going to have much motivation to stick together as opposed to covalent bonds in which electrons are actually shared. So I'm going to show you guys a little animation that shows how electrons are literally transferred from one positive section to a negative section. Okay. That will cause the Na to become slightly more negative and the Cl, sorry, slightly more positive and the Cl to be slightly more negative. And hence they will create the infamous table salt situation here. All right, so we kind of have an idea of what covalent bonds look like in terms of electronegativity as well as ionic bonds. We'll get through a couple conceptual questions here for you guys. Okay. One is regarding fluorine. So I will actually pop in both of these questions for you. Whoops. Okay. Maybe just the first question. Okay. Let's say if lithium and fluorine react, which one would have more attraction for an electron? So AKA they're reacting, they're forming some sort of molecule or compound bond. So I'll give you guys a minute to pop this into the chat box. These questions are extremely straightforward, so hopefully we can push along here. All right, I think the answer was kind of given a little bit earlier, but let's try out the comparison between fluorine and iodine as well. Okay, and again, we want to think about why. I don't really expect you guys to understand the mechanics behind why, but you can always make a good guess. Okay, well, it would still be fluorine. As we know, it is the greediest compound. But the reasoning is a little bit different, right? So over here, the reason fluorine is more electronegative is because it has more protons, right? We're going horizontally here. So fluorine has more protons. Those protons are going to be really wanting to pull in a lot of negative electrons from outside, okay? Now, why is fluorine stronger than iodine? Okay. The nuclear charge of iodine is greater, but its valence electrons are at a higher principal energy level, right? So because the N value is so much higher, those electrons will actually shield one another. So the outer electrons are actually going to shield the inner electrons from really interacting, okay? So those are very like deeper reasonings behind why electronegativity is the way that it is. Let's try another concept check. Again, general trend, we've already figured this out. We don't really necessarily need it anymore. But if there's anything that you want to take a screenshot of, I think this would be it, right? The relationship between electronegativity and bond type are very basic. As you can see, this is table 8.1, right? And what it really means by character is, just the properties of the molecule, right? The properties of the combination on a macroscopic scale, right? So very similar to the number line diagram that I had shown you guys earlier. And with regards to comparing delta EVs, right? We've got hydrogen being compared with all these other elements along, these are, I think, pretty much along the same row, right? Sulfur, chlorine. Oh, maybe not actually. They're not in the same row necessarily, right? But we do have in parentheses the electronegativity values for each of these elements. Okay, so obviously hydrogen, H2, that's going to be a fully covalent bond. They're just sharing that one electron with each other. Feels good. This one has a very small difference, and over here we've got a very large difference. So hydrogen is a bit of an anomaly. It actually has a unexpectedly large EV value of 2.1. But as you can see, if it connects with fluorine, it's going to be a very ionic-ish bond. I think this is a difference of nearly 2. So this would actually be defined as an ionic bond, right? And so getting those categories down, right, using the 1.7 and the 0.7 as your, break-even points between what's ionic, what's polar covalent, what's fully covalent, is really all you need to know here, right? So if I were you, I would make sure that you have a reference sheet out, okay? And in fact, you could probably even screenshot this one, if it's helpful for these next example questions, since this one is a little bit easier to read. Okay. And I think for some of these questions, you can probably guess what the values are. Let me dip in here, right? You can probably guess just by using the periodic trends. But again, for elements that are very close to one another, okay, left, right, close to each other, you'll want to look at the actual values, right? And actually do the subtraction and find the difference. Okay. So let's say we've got some rankings here. We want to go from most polar to the least polar for each of these. And honestly, we can probably skip out on this last row. Actually, no, let's skip out on the first row. Because I'm trying to make things as, I'm trying to avoid repetition here. So let's get rid of all this fluorine business. But check out your reference table and try to do the calculations here, right? So go from most polar, which means most ionic, to the most covalent, basically is the translation here. So I will give you guys a couple minutes to work on this, maybe 3 minutes. Okay, let's see how well you understand this.
I have a question. So
I think.
when you determine like the difference in electronegativity, the smaller the difference is less polar, right?
Yeah, the smaller the difference, the more covalent. Yeah.
Okay.
So the wording is weird. I mean, most means ionic, least means covalent. So sorry, my mouse is not. So I do want to see just some rankings here. Once I get maybe 4 or 5 responses, that would be ideal. So we're skipping over part A. All right, getting some direct messages. Again, don't be shy, especially if you agree with these responses. Okay, so for the sake of time, I'm just going to reveal parts B and C. I think the ClCl one is pretty obvious, right? It's super covalent, right? Although B and S, they're kind of close to each other. So you actually have to look at the values in your periodic table or trends table to just kind of examine and see, okay, this one is a big difference, this one's a small difference, and put them in order. Kind of a time-consuming process, but it is what it is. Okay. And then we've got one more question that I want to figure out here is, which of these following bonds would be the least polar, but still be considered polar covalent? Okay, so not quite fully covalent. We want a value that's maybe somewhere around, 0.7 to 1, right? All right, we are kind of running out of time here, so I think I'll point out that it is nitrogen and oxygen that have a very slight difference in electronegativity values. Okay. All right. Well, hopefully that was productive for you guys. If there's no last minute questions, I will go ahead and see you guys tomorrow morning. All right, bye-bye.